Fantastic. Guys, thanks for coming out. Always appreciate it. It's good to see people tuning in from around the world. And today we are lucky enough to have the multifaceted, multi-talented Charlie Beard here with us, who has a range of expertise that I found out recently. So he uses experiments, natural samples, numerical modeling to look at magmatic processes and evolution across the mantle. And the reason why we're interested in that today is that he looks at critical metals that are good for renewable energies and these high-tech raw materials, right? So he started off doing geology in Bristol, and then he smartly moved over to the Great White North of Canada, where he did a master's at UBC in Vancouver, and then he moved over to McGill doing fluid experimental petrology. So he's looking at mineral melt partitioning, and that was in collaboration with the GFC Potsdam. He then had a stint at a British Geological Survey working on the HiTech AlkCarb project, which is what I'm sure we're going to hear about today. And now he's a postdoc at Sisprobe at the Grenoble Alpes. So he's been working on passive seismic techniques. So you can tell that this dude knows apparently a lot about a lot, and hopefully he'll share a lot with us today. So welcome, Charlie. Thanks very much for offering to do this. And when you're ready, share your screen. Let's do it.
Thank you for the introduction, Chris. So everyone can see that screen there? That's good. Yeah. Super. Okay, so yeah, today I'm going to be speaking mostly about work which was done as part of the HiTech AlkCarb Consortium, which ran from 2016 through to the beginning of this year. And the reason for that really is because the whole of our community is moving towards minerals for climate action. So there's a big World Bank report which came out last year, and many of these conferences have popped up in the last few years, and government initiatives such as the EIT Raw Materials, Resources of Future Generations, even the Mineral Deposit Studies Research Group here in the UK ran a Metals for a Green Future this January. And so many different consortia have come out of this. These are just a few which collaborations of mine or myself have been part of. So HiTech AlkCarb, SOS Rare, EU Rare, and then now INFACT and Pacific, which are low impact exploration technique projects also funded by the EU. So the reason that we're doing this is because we need to decarbonize. So for example, wind turbines here are getting larger and larger, and their power outputs are increasing. So for example, a single 3 megawatt turbine requires all of these materials. So some of you'll be familiar with: copper, steel, concrete, aluminium, and then rare earth elements, which are kind of the new kid on the block. So in the past, demand for rare earth elements was very, very low, but they have excellent magnetic properties. So they are used in these neodymium iron boron magnets. You can see here in the top of one of these wind turbines right here. So we're typically thinking about 200 to 500 kilograms of neodymium required per megawatt of generating capacity. And over here we can see a forecast demand by Roskill in London for the various rare earth elements here. Another great use of them will potentially be electric vehicles, so electric cars, electric bicycles, electric trucks potentially, because the motors need these magnets. So alkaline carbonatite systems are also major sources of other raw materials. So here, phosphorus for fertilizers, fluorine for catalysts and coatings, and then niobium and scandium, which are often used in high performance alloys. So a little bit of background on the HiTech AlkCarb Consortium. So it ran from 2016 to 2020 with about 40 people at 12 institutions spread across Europe, and also we had some partners in Southern Africa and Namibia. And one of the things which we were trying to do here as part of my project there was to homogenize some of the local nomenclature used in alkaline silicate rocks and carbonatites. So typically in the past, there wasn't a great demand for these sorts of raw materials. And so they were the playground of mineral collectors, and mineral collectors love naming things. So we wanted to homogenize some of the local nomenclature between groups in Greenland, groups in Russia, groups in Africa, and make sure that we were comparing like with like. Secondly, we wanted to catalog some of the relationships between different rock types and work out the shapes and sizes of units so that we can be predictive and use that to feed into some exploration models. Speaking of which, we wanted to develop a scale-dependent exploration strategy which looks at different processes and techniques depending on what size one is looking at. And also that will include environmental, social, and engineering considerations. So I'm just going to start out with some quick definitions here. What is an alkaline rock? What is a carbonatite? So the term alkaline is used pretty widely and pretty broadly, but typically it means that we have normative alkalis, amphiboles, or alkali CPX in the rock. The slightly more strict definition here is per-alkaline, which is a chemical definition, which means that we have excess sodium and potassium over aluminium in a molar quantity. So what this means is that pretty much any mineral that you crystallize, be that even feldspar, you're going to increase the amount of alkalis in the residual melt. This means that the melts stay very low viscosity, down to low temperatures, and it also depolymerizes the structure. So high field strength elements and rare earth elements stay in the melt during crystallization. You may even get carbonatite in some of these cases, which is a igneous carbonate rock, typically defined as containing more than 50% igneous carbonate minerals. And so on the left here, I've got a diagram here from Max Schmidt and Daniel Wiedendorfer in geology. And this is just a load of major element plots for oceanic island systems, which either do or do not contain carbonatite. And these are strongly alkaline systems. So we can see you've got your typical basalt through to rhyolite down here. And then here we've got basanites up to phonolites on this left-hand side here. Two things I want to point out here. We've got an alkali feldspar thermal divide. So in the phase diagram of this system, if you have higher alkalis and lower silica, when the melts are evolving along these liquid lines of descent, if they hit this side, they'll go towards the phonolite minimum, sorry. And if they have higher silica, they will go towards the granite minimum, and you'll end up with A-type granites or pantellarites. Another thing I'd like to point out on this diagram here is this maximum extent of miscibility gap, which is experimentally determined. And this is where you start getting carbonate melts exolving from typical silicate melts. So there's a few different ways of generating carbonatites, but one of the most popular ones, which is bandied about in the literature now, is that you have a silicate melt forming from the mantle, and then that will evolve and eventually will saturate a carbonate melt, which will separate from it by miscibility. So just to show you some of these things in the field. So on the left here, we have a banded carbonatite from Tundulu in Malawi. You can see that there's a lot of lineations and structure within this, which maybe suggests some subsolidus flow. And then on the left, we have an agerine nepheline cyanide. So this is from Voisey, also in Malawi. So these will look typically the same as granites in the field. Right, so now I'm going to talk a little bit about the mineral system concept. So the oil and gas industry has been doing this with great success since the 1970s. And what they do is they'll take a system and they'll look at the energy, the ligands, the source, transport and trap of the metal or commodity in interest, and outflow of any residual fluids. So certain processes within this mineral system will be relevant at longer length scales, as we can see here with the regional scale components of 5 to hundreds of kilometers. So typically the energy, ligands and source and transport will be more relevant at longer length scales. Whereas when we're down in the deposit itself, we're interested in trapping mechanisms. So what we can do is we can define mappable criteria for each of these different processes, and we can check and see what's going on in our system. So this isn't for geology, this is for not all whiskey, this is for American whiskey. But what we can see is we've got these decision trees, and we can use these to say, well, I'm at this stage, so I'm potentially, do I have ligands or not? And I can say, oh, well, I'm down this path and there's no ore deposit on this path. Therefore, I've de-risked all of the stuff on the other end of the system because I've taken out all of the possibilities down here at one end. So there's one thing which is not in that decision tree there, and that is the risk to a project of people, or the risk of a project to people. And one of the things which we did in HiTech Outcarb, mainly with Alex Spicer and Kate Smith, who I believe is here now, is we ran public consultations with communities around potential projects for rare earth elements. So Lofdal in Namibia is one of the projects we work with. And so there's a balance here. We've got potential community benefits from mining, which are shown in this word cloud on the left. So development, people, skills. And then on the other side, we have potential health risks, dust, concentrations, mining, and this sort of thing, and uranium potentially. And so radioactivity is one of the things which we need to be very careful about in these sorts of deposits, because uranium and thorium will often associate with the rare earth metals in these sorts of deposits. And we need to be able to deal with that in a socially responsible way and ideally use it as a byproduct. So another thing in terms of engineering considerations is there are 233 rare earth minerals defined by the International Mineralogical Association. And right now we only have processing technology at a commercial scale to deal with 5 of those: bastnäsite, monazite, apatite, loperite, and xenotime. So this cuts out a fairly large number of the major deposits that we know in the world as being potentially commercially viable right now. Processing technology for minerals such as eudialyte, which is a complex sodium zirconium silicate, and the main ore mineral in some of the large deposits in Greenland, are currently being worked on. Another process which we want to talk about a little bit, but is not the main focus of this talk, is weathering. So weathering's great because it breaks down the rocks and reduces the amount of energy required to mine. One can potentially go into one of these laterite systems with a backhoe and pick up a big clod of soil which has the rare earth minerals in it, and then sieve it and separate those minerals, and then you're pretty much good to go. So another thing which is really good here is potentially you have residual enrichment, where most of the major rock forming minerals are dissolved and taken away, and the rest is left. Another thing which is important to think about here is redistribution of the commodity. So some commodities here will be soluble in waters, and so they can be either moved through the profile and concentrated in certain places, sometimes in minerals which are difficult to chemically process at a later stage. And so the SOS Rare Consortium is worth checking out if you want to learn a little bit more about weathered rocks and niobium and rare earth element deposits. So I talked a little bit about energy there, and one of the things which is cool, which has come out of this project and partners of that, is using life cycle analysis to compare projects directly. So Rob Pell, who was doing a PhD with Francis Wall at Camborne School of Mines, has now made a spin-out company called Minviro. This is just a couple of tables and figures from their 2017 elements paper, comparing various different types of rare earth source. So we've got mineral sands, iron absorption clays, which are used in southern China, alkaline rocks, weathered carbonatites and carbonatites. And we can see that the amount of rock varies, the byproducts potentially vary, and the amount of energy varies. And this is just greenhouse gas emissions in equivalent CO2 kilograms per kilogram of rare earth elements. And we can see that bastnäsite is much more efficient there than monazite, for example. So back to the mineral system. We're going to now work at the largest scale, so tectonic setting. And we're going to compare the sorts of different deposits which one would find in different settings and what factors might change the prospectivity at that scale. So we need a global compilation for this. Fortunately for us, Alan Woolley has dedicated his career to publishing largely these 4 huge volumes, which are compilations of alkaline rocks and carbonatites of the world. Now all of these have been made available online in a searchable database, which is available at this website up on the top left, which we'll put in the YouTube comments. So what we can see here is in blue, we've got spots for alkaline silicate occurrences, and in red, we have carbonatite occurrences. And we can see that the carbonatites especially tend to be clustered around areas of thick old Archean crust on the margins of cratons, as we see here in southern Africa, and that we have lots of alkaline silicate rocks and carbonatites associated with slow rifting. So for example, the East African rift down here. What we also have is some collision-related deposits, which I'll jump into a little bit more here. So what we have potentially collision-related stuff here, where we have material potentially coming down a subduction zone, metasomatizing the subcontinental lithospheric mantle, enriching that with ligands and the commodity of interest, the rare earth metals and the niobium potentially. And then when the origin is finished and we start having decompression melting during collapse of that origin, we can have these post-collisional complexes placed into the crust. Alternatively, we have these continental rift type magmas, which I'll talk about a bit more soon. So post-collisional magmas, the main deposits which are mined currently today are in the Cenozoic mining Jichang belt in southern China, and it's just on the eastern boundary of the Himalaya. So these are plate motion vectors here from Berkeley Seismology Group. So this is the second biggest rare earth mine in the world right now, Mao Nuping. Typically, these sorts of deposits will have a lot of potassium from the subduction zone. They'll be rich in carbon, so a lot of carbonatite. Barium, fluorine, and FO2 are also high, and the mineral deposits tend to be rich in light rare earth elements with little amounts of niobium and tantalum. By contrast, in rifted settings, we typically have these longer lived systems potentially, and a fairly narrow range of depths where the deposits are. So the Gardar rift in Greenland is about 3 to 5 kilometers of paleo depth, and it has these beautiful layered cyanites, as we can see here on the image. So these sorts of settings typically have more potassic magmas. They're also very high in fluorine, and they tend to be heavy rare earth enriched and high field strength element enriched. They have low carbon, so not very much carbonatite, if any, and low FO2. So these things are everywhere. The EU Rare project was looking at where in Europe we can potentially find rare earth deposits, and here is a compilation map from Catherine Goodenough, who I believe is in the audience. So yeah, we can see all over Europe we have these sorts of belts. And in time, we also have variation. So this is a fairly preliminary diagram here, and we would like to work on this a little more and compare it with the amounts of continental crust that we have through time. And I believe that that's being done right now by Alan Woolley and Emma Humphreys-Williams at the Natural History Museum. So, right, we're at the tectonic scale. The critical components we're looking at here is low degrees of melting, potentially for a long period of time, and potentially a fertilized source from subduction. We don't really fully understand the role of that yet, but here is just a compilation of different types of sediments going down modern trenches from Terry Planck in Treatise on Geochemistry. And we can see enormous variations in this. So potentially what one might be able to do is, if we find that certain sediments are conducive to mineralization because they have a high amount of the commodity or a high amount of the ligands, and that's recycled into these post-collisional deposits, we could then say we have this ocean basin with that type of sediment which subducted in the past, and this post-orogenic area nearby is more prospective than that second one, which didn't have that right type of sediment. So that's ongoing work which we're doing right now at the BGS. So now we're going to zoom in a bit. We're at the province scale, and we go back to this mineral system. So on the tectonic scale, we were mostly looking at 1, 2, and 3, so energy and ligands and source, and a little bit about transport. And right now, when we zoom in a bit more, we're looking less about ligands, less about source, but a lot about transport, and a little bit maybe about traps and outflows. So we can use airborne geophysical techniques to map crustal permeability. This is some total magnetic intensity images on the left of Dronning Maudland in East Antarctica under ice cover, and then on the right-hand side, an interpreted geological map of that. And so what we can see is that we've got sutures, and we've got lineaments and structural trends which can be picked out through this, this magnetic data. Typically also flown with the magnetics, which are good for working out permeability structure, is gamma radiometrics. So this will tell you about the thorium, uranium, and potassium concentration of rocks within the top 30 centimeters or so of the surface. And you can use ratios of those to tell you a little bit about which sorts of alkaline-silicate or carbonatite rocks you might expect to see in that area. So what sort of geometries are we talking about on this length scale? So the Gardar province has intrusions closely packed, bordering a major rift system about 60 to 100 kilometers wide, whereas the Damaraland province in Namibia has intrusions distributed along trends perpendicular to a rift, which is defined here by the coast of the South Atlantic Ocean. In these post-collisional deposits, such as the Mayan-Gichang belt, which I showed before, it's more like the Damaraland province, and that seems to be more commonly the geometry which one would see than the one on the left. Okay, so wall rock influence is another thing we can look at on this length scale. Country rock is very important because it affects the sort of alteration assemblages which one might see, and also it can influence the type of possible deposits. And the data for this are available from surface geological maps, widely available from government surveys. So here on the left is a diagram showing various different types of phenite, which is altered rocks associated with carbonatites. And this was put together as part of the HiTech AlCarb project by Holly Elliott. What we can see here is on the inside we have carbonatite. Close to the carbonatite we have a zone of potassic phenite breccias. So these will be dominated by K feldspars. And then further out we have sodic phenitization, which can be localized along veins, which is typically characterized by sodic pyroxenes like agerine. So also what we can find out from some of these regional maps is erosion level, which can be very important to determine what sort of deposit we'll have. So just going back to the slide I showed earlier, East African Rift, the modern system, and then the Gardar Rift, where we have the mineralization exposed and a erosion depth of about 3 to 5 kilometers. So now I'm going to move quickly into what we did at the district scale with these 3D geological models at about 15 kilometers length scale. So now we're looking at the trap in this mineral system, a little bit of the transport and a little bit of the outflow. And there's a few different types of deposit that we can have depending on the geology. So historically, this has been done very, very well in Russia by a guy called Frolov, who nearly 50 years ago published this compilation of different types of mineralization found in ultra-basic alkaline rocks and carbonatites. So what he did is he took surface geological maps of as many complexes of this type as he could find, where the tectonic setting and the overburden removal was known. And so this is on passive continental margins, where overburden removal can be known. Whereas in orogenic belts, so the example of the Mayan-Gichang, this cannot be done because the structural setting is too complicated. So what we can see here is that we've got volcanic complexes, such as Napak, Songwe, these sorts of things here. And then we go down to these deep ultra-abyssal features, including things like Silbijari, Jakiporenga, stuff like that. So what Frolov did was he put different types of mineralization on this vertical scale here to show what types of commodity one might expect depending on where they are. So we've been able to take that a little bit further, fortunately, but we have used a similar approach. So we've taken surface maps of as many complexes as we can find, made the scale the same, and mapped each rock type in the same way. This is slightly more complex lithologies than the first one. And we've also been able to use 3D geophysical techniques and 2D geophysical techniques to help us inform that as well. So for example here, this is some magnetotelluric images from the East African Rift published in GRL in 2018. And what we can see is these high conductivity regions here at depth, which are interpreted as large magmatic systems in a sort of layered transcrustal magmatic system. And then we have a shallower body here, which is at about 3 kilometers depth. And this seems to be consistent with some of the limited information we can get from petrogenetic indicators of depth and chemical equilibrium from pressure from minerals in some of these complexes. Additionally, these sorts of deep, dense anomalies that we can see on the right here are consistent with deep, dense gravity anomalies in this 1978 report on the Gardar province in Greenland. So we think they might be reasonably well distributed. I'm just going to talk briefly about some of the relationships we see within these sorts of complexes before we dive into 3D. This is the Motzfeldt complex in the Gardar province of Greenland, which Adrian Finch and his group at St Andrews have worked extensively on over the last couple of decades. And what we see is we see these arcuate shapes of units, and we see progressive intrusion further inwards generally, and we see progressive decreases in the silica content with time, potentially due to decreasing contamination from sandstone wall rocks. And we see increasing alkalinity, so that's the molar alkalis over aluminium with time, which is tracking increasing fractionation of the magmas. So that's dropping out of all of those mafic phases and residually enriching those commodities we're interested in. So I'm just going to throw the 3D PDF now. Okay, so on page 1, we have some instructions and a short description. And we can click on the instructions thing here, and this has some quick directions for how to use the PDF. And then we can go to the geological model. So on the left side here, we have various different controls of the components that you want to turn on and off. We can turn off each corner independently, and there are a few predefined views which we can show here as well, which we'll zoom between. So the idea here is to give a bit more spatial reference frame to where we're at in these sorts of systems. So we've got at depth, oh, sorry, let's just go back to that. So at depth, we have this layered magmatic system, which is inspired by those MT images from the East African Rift and the gravity anomalies that we see in Greenland. We have a big, in red here, shown a transcrustal fault system. So this is guiding the magmatic ascent towards the surface. And that's long-lived, and that's opened up several times during the evolution of the complex. Near surface, we have a caldera and a ring fault system, which is seen in many of these sorts of complexes and tends to define the shape of the systems themselves. In blue here, we have one of the earliest stages of intrusion here, which is weakly alkaline and full of these xenoliths of basalt, which is part of the country rock. So this is defined by the Motzfeldt intrusion, which I showed previously. In yellow here, what we can see is these are the sandstones. And in the top here, we see a roof complex, which is where alkaline magmas from the intrusion are reacting with the country rocks to form this separate layer of silica-saturated granitic magma in the roof, which is very rich in fluorine and all of those metals which are in the residuum from crystallization of this lower part here. I'm just going to show the mineralization details here. So we can click on this mineralization details bubble here, and it shows some field photos and some hand samples and a grade tonnage diagram. So this is prospective for niobium in Motzfeldt here. And there's only one type of this deposit which is currently being explored. So once the system has evolved a little bit more, what happens is the wall rocks are then physically isolated from the magmatic system as we have evolution of the system and rejuvenation over and over again. So with time, the silica concentration in the magmatic system tends to go down and the alkalinity tends to go up. And we end up with different types of mineralization in that sort of sense. So here, I'm going to click again. This is layered alkaline suites. So these will typically be higher in alkalis, lower in silica, and some of the largest deposits that we know of rare earth elements. So this is a grade tonnage diagram here again, but this time rare earth elements. And here on the right here, we've got Kjarnefeld and Kringlerne, which are in the same intrusion, in the Illimausak intrusion in Greenland. And we have Lovazero in Russia and Nechalacho in Canada. And these are all fairly large systems which have eudialyte, which is this image here. And this is that complex sodium zirconium silicate, which I spoke about briefly earlier. And unfortunately, there is not currently processing technology for this at a commercial scale to extract the rare earth elements, but it's in development. These sorts of systems are also interesting. Sorry, I click back into that. These systems are also quite interesting because they're heavy rare earth enriched rather than light rare earth enriched. So they're shown in the purple here. And the heavy rare earth elements are slightly more valuable because they're used in the magnets to make them withstand higher temperatures, which is very important in wind turbines. Okay, so in some cases as well, we may have these roof zones of silica saturated magma escape the system. And in those cases, they could be emplaced. And we have a few examples around the world where we think this may have happened. And that's shown in this pink here. I'm just going to zoom into that. Where's the granite? Yeah, there we go. Okay, so what we have here, we have emplacement of the granite from one of these roof zones which gets tapped, and separation of a fluoride melt which rises to the top of the granitic intrusion and is emplaced in the roof. Now, there's some really cool studies which have come out of McGill from Olga Vasyukova and Anthony Williams-Jones, which have looked at this in great detail. And they've even found macroscopic fluoride melt inclusions, which are about the size of your fist. Really, really cool stuff. And so what happens is the top of the system here ends up being rich in calcium, rare earth elements, and high field strength elements and fluorine because of these fluoride melt separations. Whereas the lower parts of the system are slightly less enriched. I'm just going to go back to the mineralization view. Then we can click on that and look at that in a little bit more detail. Okay, so here we go. So these deposits are usually slightly smaller than those alkali-silicate layered systems, but we might be able to process the minerals in those. Right, okay, cool. So that's a rough overview of this 3D PDF model. This will hopefully be available soon. We're currently preparing this for submission for publication. Right, I'm just going to jump out of this quickly and we're going to go back to the slides. And I'm going to talk very briefly about carbonatites. Just go back out of this. Okay, so in terms of carbonatites, we have a lot of variation with depth, which was fairly visible in the Frolov model from 50 years ago. And we have a little bit more information today, especially from deep geophysics and also from deep mining operations. So one of the really cool operations here is the Palabora carbonatite, which is currently mined for copper in South Africa. And we can see strongly vertically foliated structures in these sort of carrot-shaped intrusions. And we see zonation of different rock types with depth as well. So this is from Johannes Giebel, who is doing his PhD at Tübingen. On the outside at depth, we have silicate magmas and silicate rocks. So this would typically be pyroxenites or very olivine-rich rocks. Then we have this weirdo called phosphorite, which is thought to be an immiscible melt, which is rich in phosphorus. And it makes phosphorus and olivine rocks, typically. And then we have these carbonatites, which may be more buoyant, which come up towards the surface. So in plan view, many of these systems look fairly similar. So they're typically circular or oblate in plan view. And you typically have cyanites on the outside. Then you go in towards calcite carbonatites, dolomite carbonatites, then iron-rich carbonatites. And the concentration of rare earths or niobium typically increases inwards along this sort of trend. So I spoke briefly about the depth control and mineralization type. So we're preparing that a little bit right now with an MSc student who's doing some work with Francis Wall in Camborne School of Mines. So just to finish, I'm going to briefly show you 2 minutes of a video which we prepared as part of the project on one of our main studies, which is the Kaiserstuhl carbonatite in southwest Germany. And this will give you some ideas on the geometry of these sorts of systems. See if I can get the sound working for it as well. Right, so I've got to go through to here. Share computer sound. So I'm not going to show the whole video, but it's available on YouTube if you want to watch it.
It is into these rocks that the Kaiserstuhl was intruded 18 million years ago. Using three-dimensional gravimetric and magnetic data, shown in black and red, it was possible to characterize the different intrusions and project these to a depth of 3 kilometers. The coincident gravity and magnetic anomalies indicate an upended urn-shaped intrusion beneath the known sodalite Monza gabbros and carbonatites. Other intrusions are the phonolites in red, vertical pipe-like intrusions which erupt rapidly and expanded near the surface once the lithostatic load was breached. In purple, the Limburg intrusion, which contains mantle xenoliths brought to the surface from depths of 30 kilometers or more. Hidden beneath the lavas are geophysical anomalies indicating unknown intrusive or extrusive rocks. These almost horn-like extremities are roughly orientated along the Tuniberg fault and are similar to features observed at the Vulture volcano in Italy, suggesting these rocks are part of an early caldera or diatreme collapse structure. For the final part of the puzzle, we moved into the most detailed prospect scale. It is at this scale of investigation where we explore in the field. Shown are the results of an electrical IP survey which indicates in red where electrically chargeable minerals such as sulfides occur. We know deep weathering is necessary to upgrade deposits of niobium and rare earths, so the place to look is where weathering is greatest. The zone cross-cut by the Tuniberg fault shows the deepest weathering, and indeed, samples collected from here reveal the most significant rare earth mineralization recorded in the Kaiserstuhl. This project has now laid the foundation for the application of a mineral system approach in the exploration of critical materials hosted in carbonatite and alkaline-silicate rocks.
Okay, so with that, thank you very much. And yeah, I hope that was interesting. And if you have any questions, please feel free to ask.